So let's start. I will give you an overview of the structure of the talk. As you can see here in the subtitle, and as has been mentioned twice already, the talk is about OCaml. So we will have a first quick section about OCaml itself. And then here in the title, you can see this word magic, which alludes to Merlin. Merlin, you probably know Merlin as a nice musician, but we also know Merlin as a very nice tool in OCaml that brings nice editor support to OCaml. So the second section is about this tool, Merlin, and about its performance. And then the next section will be about how we used OCaml 5 to improve Merlin's performance. So OCaml 5 is this quite recent major release of OCaml that brought parallelism to OCaml on the level of the runtime. And with it, a few very nice mechanisms, notably effects and effect handlers. And we will tell you about how we used these new concepts to improve Merlin's performance. And then there will be a last section where we talk about the performance impact our work really has, and about a few bumps in the road that we have hit throughout the work. And I do want to give a heads up. So the work we are presenting is still experimental. It's currently on an experimental branch of Merlin, not merged yet. But still we have a lot of interesting takeaways from it already. So let us start with the first section, the section about OCaml. I will go through this very quickly. OCaml is a functional language, not surprising, but it's also multi-paradigm. So it has a very nice non-steep learning curve at the beginning. It's very nice to get started with. And another very nice thing about OCaml is that you can always add these nice camel GIFs to any presentation. They light up a bit the mood. And, but a bit more seriously, there are more camel GIFs. Okay, but now really. So OCaml has a, smallish, but very solid and stable platform and ecosystem. The tooling around the compiler is solid. We have a well-built, well-maintained, mature package ecosystem. And in general, there are no big challenges in the road when you use the language. Now to come to applications and strengths. Last section here, not without a camel GIF, of course. So you see that OCaml is a very versatile language. We have a lot of different kinds of applications. The language is particularly well known to write compilers, but it's also a very nice language to do web development, full stack web development. And you can even do lots of stuff like even hardware stuff with it. So this has been my quick run through the OCaml section. Oh, another nice gift, by the way. And now I'm coming to what the talk is about, Merlin and the magic of Merlin. I will start with a live demo about it. Oh, yeah, I should probably go to do the live demo. So here you see a window of the editor VS Code. And inside VS Code, I have opened a real OCaml project for you. I have just added a few comments to this file for the sake of this demo. So the demo, I'm going to structure it into two parts. The first part is a short one about OCaml again. And then the second one will be the major part of the demo about Merlin and its magic. So for the part about OCaml, you can have a look at the first two lines of code. So OCaml is a functional language. You can see here in the first line a type definition of a product type. So OCaml has ADTs. It also has GADTs, by the way. Here you can see the syntax for a function definition. So this kind of syntax invites a lot to do function currying and just really treating functions in a very functional way. Now if we go to, okay, with one hand it's harder. I will do it with my mouse. To line 23. You can see though also that it's not purely functional. You can also perform side effects in OCaml. So there you see a function whose only purpose is to perform a side effect. And that is possible and it is okay. You don't need to wrap those things into a monad or anything. When there's a good reason for it, and only then please, you can perform a side effect in OCaml. And now we will get already to the last feature I want to highlight here, which is modules. So modules is a very interesting concept in OCaml. It's quite unique to OCaml, I think. I think it's not very, I don't know if there are other languages that have it, outside of the OCaml family. So modules, for one, are a way to namespace your values. So for example, if I wanted to access content length, I would do so via private.key.content length. But that's by far not all. So modules can be treated as values. So the concept to namespace your values can be wrapped into any data type. For example, you can make a list of modules, iterate over it, and it's just a very nice functional way to structure your OCaml program. I think it's a very interesting concept. But yeah, this is all I wanted to tell you about OCaml. And I've noticed we've done this wrong thing with the mic. So the demo with one hand will be really hard, but I will try. Let me come to the part about Merlin. I wanted to talk about Merlin, right? So what is Merlin? I've already told you Merlin is the tool that brings editor support to OCaml. So of course, editor support means things like, well, you hover over values, you see the type and the documentation. You can also jump to a definition. You also have all these types inlined here in the editor and so on. Those are basic features that exist across pretty much all languages, and they also exist in OCaml, right? But now, there are also very nice OCaml-specific features that Merlin provides. Okay, this is a bit annoying anyways. For example, you can construct a GADT via your editor. Oops. I need to say here what the type is then. If not, my editor doesn't know. So here, I haven't done anything, but I am constructing the whole ADT, the whole value, just with my editor. Right. And I can do the same thing even if the ADT is nested. So here I've jumped to a different file. Here you see an ADT that is nested, and I can show you the same feature again. And I will construct the whole ADT down to the leaves of the node. I could keep on going, right? So this is a very nice feature. It's very ADT specific, not exactly OCaml specific. We can also do the counters part. So I have just constructed a value with the editor. We can also destruct a value in a match. And in we can destruct the scrutiny of a match. And there are also a lot of other very nice OCaml specific features that Merlin brings. So here, if you open the command plate, you can see all these nice OCaml specific features and so on. So yeah, the takeaway is Merlin is amazing. It brings a lot of features. Those of you who know Spanish, I don't have a grandma, so I can say that. But I haven't really told you yet what Merlin is really, right? Like, how is Merlin connected to editor support? For that, I need to explain you how the editor works. And this is the same in all languages, okay? Like, how does an editor in any language provide you with all these nice features it provides you with? So what it does is it spawns a local server called a language server. And then the editor just delegates all complicated code analysis to that server. And the server answers to the queries the editor sends. I have prepared a setup here so that you can see this editor-server communication in the output panel. So here you see the different queries going to the server, and then the response coming back. Give me 1 second. Okay. So okay. Sorry, I have filtered something. It's really hard with one hand. I'm sorry about it. Okay, so there you go. So here you see all the things. And you don't only see the queries, you can also see in the response from the server, you can see timing information down here. Okay? So this is the time that it took Merlin to respond to this last query. And this is super fast, right? If we have a look here, 13 milliseconds, it's super fast. Meaning there's no performance issue in Merlin. We can go home. Thanks for listening. Just that it's not always the case. So this here is very small and also a pretty simple file. If we go to a file that is the opposite, a very long file, then, so let me have a look here. This file is over 55,000 lines of code long, right? That's a very, very long file. And not only that, it has a lot of these deriving annotations, meaning that from the point of view of Merlin, it is even much, much longer than only 55,000 lines of code. So it's a huge file. So now let us have a look how performance looks like in this file. Let us first just look up a type again. Here, I'm hovering over this type. And it's quite fast. It's not a big deal. I can also here do a jump to the definition of this yo-JSON of T. It takes a bit longer, but it's already there, okay? So this still seems like it is kind of okay, the situation. But notice that right now I have been doing all these queries without modifying the code in between. That is not a very real-life scenario. So here Merlin is, it gets most of the information it needs from cache. That's why it's still quite fast. But now what happens if I modify the code and then I look up the type again? So then you see this nice little no loading banner. And I'm a very distracted person, so I'm already distracted. You know, I walk away from my code. Okay, there I get the answer. But I mean, this is very disturbing, I want to say. So this is something that is, we don't want to see this kind of performance behavior in our editor. So if we have a look how long this took almost 8 seconds. Okay, this query to respond. And that is just way too much. So that was the motivation for us to start the work to improve Merlin performance. So these are, just to be clear, these are edge cases, right? Like in general, performance is really good, but there are concrete cases where we just really want to improve performance to make sure the experience is always good. So this could be the end of the demo. This was the main point for the demo. There are just two more minor points I want to make now that I'm already here. One is, notice that right now I have shown you what happens if I modify the code at the beginning of the file, right? Let us also have a look what happens if I do the same thing, but I modify the code at the end of the file. So now I look up a type here, and it also takes really long. Yeah, okay. It takes, let me have a look at the timing. So maybe you have already had the right impression. This took quite a bit less of time than it did when I modified the code at the beginning. So here you can see this was 5.5 seconds. So this is still too much, but it's much faster than if you modify the file at the beginning, okay? This is due to how the cache of Merlin works, and I don't want you to understand details now. We are going to get into this later. But just as a takeaway from the demo as well, if you modify a file at the beginning of the file, this is like the worst case scenario. This is when things are the slowest. And now the last very quick point I want to show you is you can also see here in the logs that the editor sometimes sends these cancellation requests to the server. And you cannot see what the server does with them, but I'm telling you it ignores them at the moment. At the moment, Merlin ignores the cancel requests. And yeah, this is the last point of the demo. Oh, no need to do funny mic things anymore. So I will come back to the presentation. This was the live demo. There's one small thing about the demo that I haven't told you, which is the project that I did the demo on. You can have a look here. It's called OCaml LSP. And this is just one more layer in the editor support chain for OCaml. So I told you about the communication between the editor and Merlin, but actually there is OCaml LSP in between. So I thought it was a nice meta level angle to give to the demo to show you the code that we actually work on. So yeah, you have just seen OCaml LSP live, and Merlin is the back end of OCaml LSP. This is Merlin, and this is what it talks about. And this is a nice tree in Cádiz. It's, by the way, it's called the magic tree according to Google. And the reason why I show you this is because I want to talk a bit about ASTs to explain you how Merlin works. A quick question into the round. Who of you remembers very roughly what an AST is, what the beginning of the compiler pipeline looks like? Quite a few people. Okay, cool. So we can do this quite quickly. So an AST is a representation of a program in the form of a tree. And in OCaml, there are two kinds of ASTs, okay? There's the parse tree, which is the AST that most people have in mind when you think about an AST. It's an AST that only encodes syntax information. It's the direct result of parsing. And then there is the other AST, which is called typed tree. And that one is the same as the parse tree, but every expression is annotated with type information. So it's a much, much, much richer representation than the parse tree. And yeah, both of these trees are made up of so-called top-level items. So top-level items are things like value definitions, type definitions, module definitions, and so on at the level of the file. So no nested stuff at the level of the file. And yeah, both the compiler and Merlin need to build up these different representations to do their analysis on these ASTs, on these representations of the language. And that is how it looks like. So you see, you start with the source code, and then that gets parsed into the parse tree. That is what you usually understand on an AST. Then there can be some meta programming happening in OCaml that happens at this stage. For example, the deriving annotations that you saw before happen here. So this gets expanded into an expanded parse tree. And then the expanded parse tree gets typed to become the typed tree. And this is where the typer comes into place. This is what the typer does. So what the typer does, the type is actually very complicated, but you see it can be simplified into this small diagram. It just goes through the list of parse tree items. You can imagine this as a map if you're not familiar with recursive functions. It goes through the list of parse tree items, and it types every item by item. It's an item by item process. Okay? So, and here you see this pipeline that I've just shown you inside of a bigger picture. And here you see the bigger picture. And I think I need to zoom in a little bit, right? Is that good? At the back of the, okay, cool. So, this is really the whole control flow of current Merlin without our changes. So at the beginning, the server gets started. Then, the server waits for a query from the editor. Once it gets a query, it reads the query parameters, right? It needs to know what to do. If it is said, please stop, then it's kind enough to go ahead and stop. And if it is any other query, let's say any real query, then it needs to read the content of the buffer. When we say buffer, we need file, okay? That's just what we do in the editor world. We say buffer instead of file. It reads the content of the file, and then it has all the info it needs. So it goes ahead and dispatches the query to a query handler. And then every single query handler does the same thing. They all trigger this pipeline, which in Merlin is a lazy pipeline, to get the representation that this query needs. In most cases, it's the type tree. In most cases, the query handler needs the most complex representation, which is the type tree. But sometimes less information is okay, and then whatever representation is needed is returned. Once the query handler has the representation it needs to do its analysis, it goes ahead and does its analysis to find an answer to the query that it was given, right? And once it has an answer, well, it returns the answer, and then it goes up again to wait for the next query. Okay, I need to zoom out. Okay, now I want to, so this whole talk is about performance, right? So I want to tell you where in this diagram the performance bottlenecks lie. For that, I have prepared this small metrics table. So here you can see the result of running Merlin on, I can't believe it that I still haven't changed it, on a very big code base. This is a code base. We have run Merlin on 2,400 samples in this code base. And you can see here, on a cold cache, okay? This is not a very real life example, but it's good for analysis. And you can see here, if you have a quick skim through it, the very, very main bottleneck lies in the typer. Okay, the main bottleneck is the typer, but also the query analysis phase is not fast either. Okay, so those two are the main bottlenecks. So if we have a look at our diagram, this is the main bottleneck, and the query computation is a bottleneck as well. So this is the part. So this is kind of like where we started when we were saying, okay, we need to improve things. We need to improve things here and here. Let me come to one last point in my section, which is about the cache mechanism in Merlin. So I've already told you in the demo that there's a cache in Merlin. In fact, there are two different kinds of cache mechanisms. One is a very simple one. I'm not going to go into detail. It's a file cache. So it's just that files, once they are read in memory, they stay in memory and you don't need to read the file again. The other cache is much more interesting. It's the typer cache. So I told you before that this is how the typer looks like. But actually, if we take the cache into account, it looks more like that, okay? So what the typer does is that when it reaches an item that it should type, it first checks if it can draw it from cache. And if so, it does so. And this cache gets invalidated if either this item or any item above it has changed, okay? That is the invalidation of the cache. So, and this also explains why when you modify the code at the beginning of the file, things are very slow, as we have seen in the demo. Even much slower, like this is like the slowest that can happen. And this is because if the cache gets invalidated at the beginning, that's almost like acting on a cold cache, right? Whereas if you modify the file at the end, you can draw most things from cache. So the takeaway here is that we really want to speed up things when we are working at the beginning of a file. So the idea that was around for that was what was called early typing return. What that means is the following. So you can think that like Merlin right now first types the whole file and then does the analysis of on the whole typed file. But does it really need that much? Does it really need the whole typing of the file? Usually the answer is no. Usually the answer is we can just return the typing result until the queried item, and that is enough to do the query analysis. And this usually works perfectly well. There's no change in behavior. We just have a few exceptions for this. I would show you one, but it's really like edge case exceptions, and they are not a big deal. But here's one exception. You can see here is the definition of a mutable value in OCaml. And right now, the compiler and Merlin cannot infer yet what the type parameter is, right? But if we update the value to be a list of an integer, then, well, we can see it is a list of integers, right? So this is an example where a typing result of an item that comes later influences the behavior on a query of the item above. But again, this is an edge case. This is like a small change in behavior that we can live with. If this happens, you are annoyed by the weak type information, you can just run the query again. And it really doesn't happen often at all. So yeah, these are the takeaways from my section. One is we saw in the metrics table that the two main performance bottlenecks is the typer phase and the query phase. So let's parallelize them, right? We have OCaml 5. Let's parallelize those two things. The second one, we saw in the demo that currently we are ignoring cancellation requests. That is, of course, not a good idea. So let's implement a cancellation mechanism. And the third thing is what I've just told you. We want to implement early typing return. And now Carine is going to tell you how we did these things.
Yes. Thank you, Sonja. Can you hear me? Right. Yes. Great. So, let's summarize where we are in our story right now. So what we are is Merlin. We also definitely have OCaml, right? And we have some kind of a large beast that we need to deal with, which in our case are large project or a very large buffer with a cold cache. And Merlin does a lot of magic, but is not able right now to deal with it. And so, as Sonja explained, we thought of two different mechanisms to help with that, which are early type return, cancellation, and parallelism. And so this part is about how we implemented these three new magical tweaks for Merlin, and also did it work? So to implement these three new magic tweaks, we use the new feature brought by OCaml 5, which are shared memory parallelism and effect handlers. So shared memory parallelism, you most likely all know what this is about. This is the ability to have multiple core or CPU or thread running in parallel. Except in OCaml, we don't call them that. We call them domain. And so a domain in OCaml is a unit of parallelism. Domain come with their own minor heap and execution stack, so they are quite heavier than the classical pthreads that you may know about. So the rule of thumb in OCaml is actually to spawn the domain at the start of the word and then to have them waiting until you need them. And so how it works, it's quite simple. What you need in the API to run Multicore in OCaml is two functions. Domain.spawn and domain.join. So domain.spawn is basically the work that you want to give the newly spawned domain. So what it's going to do. And the domain.join function is a blocking function that is going to wait until the domain is finished with its work. So that's quite simple to use. And so let's see how we add that in Merlin to get some parallelism. So I'm not going to use the control flow graph directly because what I need is a sequence diagram, but I am going to keep the same color and the same different step. So initiation, listen, process pro-info, pipeline, and query analysis. And so the sequence diagram looks like that. So in Merlin, we have only two domains. Pretty simple parallelism. The main domain that is basically going to do everything that is related to the server part, as well as the query analysis part. Because remember, we have two parts that are taking quite long, the query analysis and the computation of the pipeline. So we would like to try to parallelism them. So one is done. So the analysis part is done by the main domain. And the typer domain, the second one, is going to do the pipeline computation. So what is happening here? So at the start of the world, the main domain starts the server, and it also spawns a new domain, the typer domain, that has nothing to do at the beginning. So it's going to wait. And then the main domain listens, receive a new query, process the information from this query, and is able to build a config value. And it will share this config value to the typer domain, so it can start computing the pipeline. So the sharing here is nothing extraordinary. It's like mutable values that is sharing between the two domains. And we use mutex to protect the writing and the reading on it. Also, we use condition and signal to get passive waiting. So nothing out of ordinary. And so the typer domains compute the pipeline. He has everything in it with the config value. And when he has finished configuring the pipeline, he will share this value, the pipeline value, to the main domain that can then do the query analysis and answer the query. And then we start again. So here we don't really have what we want, any of the magical trick that we need. We don't have really parallelism between the query analysis and the pipeline computation. We don't have the early type return or the cancellation mechanism. So let's see how we are going to use, or we used effect handlers to this mechanism. So effect handlers, you probably have already heard quite a bit about it during the conference. I think there is like 2 talks about it and a workshop. They are a way to suspend the flow of execution of execution. So they are kind of like exception, except the part of the code that is going to catch the effect. So the effect handler has access to the continuation, so it's able to go back to where the effect was originally performed. So this is a great way to control the flow of the program. In OCaml, I think the syntax is pretty nice, so I have an example here. So here you have the declaration of an effect that is called love. This effect does not transport any type of information, so it's an unit effect. But you could have a more complex type here if you want to share information in between the effect handler and the part of the code that performs the effect. And so what we are trying to do here is we are trying to print I love lambda world. So the main function is going to call the foo function that will start by printing I. And then it performs the effect love. And so it's an effect. So it's kind of like a jump. So it's going to jump until where it is caught, which is right here. So this is the effect handler. And the effect handler is actually a pattern matching in OCaml. Like it's exactly the way you will do a pattern matching in OCaml. We can catch exception and effect with the traditional match with. And so we get the effect. As I say, the effect handler has access to the continuation. So the continuation is called key here. And so what the code do then is that it's going to print the small art and call the continuation. So we are back here where we print lambda world and we have everything. So that's how effect work in OCaml. So let's see. I will explain how we use this effect to get to the magic trick we wanted. So we are back to the sequence diagram. The main domain is listening, get a new query, compute or build the config value, share it to the typer domain, that then begin to start computing the pipeline. And as Sonja explained, the early type return feature is inside the pipeline. So what we want to do here is that we want to stop the typing at the right moment. So just first thing that I want to say, the pipeline is not lazy anymore, because we want the pipeline to be entirely computed by the typer domain, not by the main domain. So we need to remove the laziness for that. And so it's still the same for step. And so when we are in the typing part, what we want is the early type return feature is this idea that when we reach some part of the buffer, we can actually return something that will be enough, like a pipeline that will be enough to answer the queries. So this is just some kind of another condition here that we check at every step of the loop if we actually have reached the point of where we can answer. If so, then we just perform an effect that will be code, but to the point of the code where we are able to compute the pipeline. So it's kind of a partial pipeline because it only has some a part of the buffer, like the part of the buffer that has been typed, but it's enough to answer the query. And so there is a thing. The typer, it only works, the typer domain, is to do the typing. So you can just call the continuation. So share the pipeline first and then call the continuation to start, to resume typing, the buffer. And so what's great now is that the main domain can start doing the query analysis while the typer domain is still typing. So we have this first magical thing that we wanted. The other good thing here is that when the main domain, the typer domain, has completed typing the whole buffer, he don't have anything else to do really, like he cannot really share a new pipeline because the main domain has moved on doing something else, but he can put everything in the cache. So now we also have a warm cache while still having the early type return feature. So that's pretty cool. So at this point, we have two of the magical tricks we wanted. We have the parallelism and the early type return. And we only need now the cancellation. So the cancellation, so yes, this is a bit more code if you want to come back to that during the question. So the cancellation, same start, right? Except now the main domain perceive a new query while the typer domain haven't finished to do the typing yet. So the main domain receive a new query and it will decide if he need to cancel the computations that the typer domain is still doing. And if so, it will send a cancellation message to the typer domain that will stop typing. Obviously, we'll also cache everything he has already typed because, again, we want our cache to get warm. And this is all because the typer domain has stopped working, is ready to move on the computation of a new pipeline. So it can just receive the config value and move on to trying to compute the pipeline required for the new query. Perfect. We have the three magical tricks that we need. Everything seems to be very fine. So it's like an happy ending. We can stop right here, right? A good story needs a good plot twist, right? Well, it's a pretty predictable plot twist, but still, it's a plot twist. So Merlin has a lot of mutable state, a lot of them. And parallelism plus mutable state is like kind of an explosive situation, right? You are going to get a lot of data races. And we did get a lot of data races. And so you could wonder, we knew from the start that Merlin has so many mutable states. So why did we even bother trying? We have two good reasons for that. The first one is that the OCaml memory model is pretty great. Data races does not mean crashes. If you will get a data races in OCaml, what you will get is like maybe you will get a 1 instead of a 2 or an empty string instead of a bonjour string, but you won't get your code like a wrongly typed value or something that is going to make your code crash. So that's a pretty good reason. The second one is Merlin is a non-critical system. By non-critical, I mean that nobody is going to die if Merlin gives you the wrong answer. Not like being in a plane. So some software to get a data races is going to be bad. But with Merlin, it's not really the case. And you can still ask again if you find the answer that Merlin gave you bad. So you can still try to get a better one. So that's two good reasons to try. The last one is it seems very fun to do. And it was. So we really wanted to do this experiment. And we did, despite the fact that we knew there were going to be a lot of data races. So we still try to find a way to mitigate these data races. And there is a very easy way to do that, right? You put mutex everywhere. So you could, in particular, the worst data races happen when the query analysis and the pipeline run in parallel, because they both change the typer state. So you can have very weird answer to do that. So there's many ways or many places where you could put the mutex to get more or less data races. It's a way to do it, but obviously we lose performance when we do that. We lose parallelism. Another bump in the road that we got, and that you may have noticed, is that the cancellation mechanism is not extremely good. In particular, it's possible to improve it. So in particular, if you get a query on a large buffer with a cold cache, and you need to type something. So at the end of your buffer, the early type return is not really going to help you. And the main domain is doing nothing when it's waiting for this pipeline. So we could definitely have the main domain listening. So it will be a chance to do it the code, and we could do that with effect handler, basically. But it's not done yet, so work to do.
So, yeah, sorry. Now that Carine has presented to you the work that we did, let me present the performance impact the work really has. I will directly show you all 3 tables I have generated due to time constraints. So to have a look at the last table, these tables were again generated in a very similar way as the one you have seen before, just that this time we are comparing Merlin with our new experimental branch Merlin domains. So here you can see the two directly in comparison with a statistical breakdown into different percentiles. And what we see down here, this is the most interesting table I'm showing you, because we see there's really good performance improvements. So a 41% improvement, it's really significant. It's very impactful. And that's really cool. So we have good reasons to be happy and to celebrate. We do also see, though, and we want to be honest here, that in some cases we do see a slowdown. And we don't know yet where that comes from. So we were not expecting this. This is not related to the new runtime model of OCaml. And this must be some small performance bug we have introduced somewhere. And we still need to analyze where it is and fix it. But in total, the improvement is much more significant than the slowdown. So in total, we are happy here with the result. So now we will come to a conclusion.
Yeah, so the conclusion is a list of questions. Don't hesitate to go back to them if you want more info on them. So is it working? Yes. Yes, it's working. And without major refactoring. Because remember, it was an experiment. And we didn't want to spend years on it. Also, we didn't want to change everything in Merlin. And so we actually didn't change a lot. And even without changing a lot, we managed to get parallelism, effect handler in, and this pretty nice feature. So that's a great win. Also, yeah, we still have databases. And are they bad? Well, maybe, because we didn't really try Merlin that much, as this version of Merlin that much, to know if maybe there is some cases where it's very bad. But it looks like it's okay. But let's be, maybe. So could we avoid databases at all? Yes, like with big mutexes everywhere, we could. Also, this will obviously completely limit the parallelism. We could also change the internal of the typer. This will be pretty bad because we will then diverge from the typer that is in OCaml, in the compiler of OCaml, and we don't want to do that. But it could be a way like getting atomic instead of mutable. And also we are exploring on a way to statically ensure data rest freedom with mod. And this is a specific branch of OCaml that is called OCaml. And that is also very fun to try. So this will ensure data rest freedom statically. Could we have done the things better? Yeah, most likely. We are exploring that. Especially we are exploring if we could have like a single core design. It will be great to compare with what we have to see if it will actually be better or not, like if the parallelism actually bring more performance or not. And yeah, what next? I already talked a bit about that, improving the cancellation mechanism, trying a single core design, trying to have a data rest freedom statically ensured by OCaml, all this type of thing. Yeah, it's finished. So thank you very much for listening. I hope you enjoy the talk. And yeah, thank you.
Thanks.